And then g of x is 1 over x. Stop talking, please. So f compose g of x is f of g of x. In this problem, g of x is 1 over x. So what f of 1 over x is going to be? 1 over x squared minus 3, or just 1 over x squared minus 3. Cool there? Okay. If I do g of f of x, that would be g of f of x. In this problem, f of x is x squared minus 3. So g of x squared minus 3 is 1 over x squared minus 3. And that's as much as you can do with that one. Cool? So one of them, the minus 3 is in the denominator, and one of them it ain't. In case you couldn't tell from my poor penmanship. Maybe that's a little clearer. Who's next? Luke. 29. Okay, it says find two functions, g of x and h of x, such that f compose g of x is h of x. You said 29. Okay. So my h of x is sine of x squared minus 1. So there's answers may vary for this one. There's lots of different, well, maybe not lots, but several different pairs of f's and g's you could use. Typically what I like to do is I like to think of like finding an outside function. In this case, that'd be like my sine x. And an inside function, like my x squared minus 1. So my outside function, f of x is sine x. And my inside function could be x squared minus 1. So if I plug g into f, I'd have sine of x squared minus 1. What else could you have done? You could have said f of x is equal to sine of x minus 1. And you could have g of x equals x squared. Right? You plug x squared into sine x minus 1, you got the above. And then you could do even simpler. Oops. This is the ultimate cheat code. So if I'm doing composition, like y equals x is just the identity function, so I just make one of them h of x and the other one x, and that's kind of cheapy, but doesn't say that you can't do that, so you can always do that. But there's probably the three most common pairs. You don't have to have all of them, like any one of these three is sufficient to answer the question. I just figured if long we're doing it, let's do it thoroughly. Is there another one that we could have done? I can't think of one offhand. There might be, though. It'd probably be something overly complicated, where something reduces down to end up with what you're at, instead of just like, oh, there, we just do the composition, and you're there. But like, who wants to do that? Not this guy. Who's next? Okay, no big deal. As always, if you come up with something else later on, we can always come back to it. It's not like once we've passed that section of homework, you can't ask about it anymore. So today we're going to finish up section 7. Is my plan for today. And I think where we left off last time, we'd just gotten done talking about composition, right? Let me just double check here. Yeah, okay. So the last thing we observed was that composition wasn't commutative, right? That F compose G is not necessarily equal to G compose X. Well, there are some situations where they can be equal. Of those situations, there's one in particular that will be of interest to us that we'll define right now. So if we say let F and G be functions, we say that G is the inverse function of F if and only if F compose G of X is equal to G compose F of X, and they both have to be X. So what are we really saying here? We're saying if you have some input X and I plug it into G, it'll give me some output G of X. If I take that output G of X and plug that into X, it'll return me X, the original starting value again. So basically we're saying that F does something to X, but whatever F did, G is just going to undo, and vice versa. G does something to X, but whatever G did, F is just going to undo. Everybody okay with that? So in this case, we have a special name for G. We call it F inverse of X. So the -1 attached to the X there is in the exponent, but we don't say that's the same as 1 over F. When we attach an exponent to a function like that, we're not talking about it like as an exponent, it's just like the name for this function. Like 2 to the -1 is 1 over 2. X to the -1 is 1 over 2, or 1 over X. F to the -1 is just, we call F inverse. If you wanted to write 1 over F of X, you'd write it this way. Just FYI. Again, want to be clear, like we're kind of abusing a little bit of notation here, but that's how we're doing it. So the mathematics world does it this way. Okay. So we've defined here kind of what an inverse is, right? It's like one function that undoes everything another one does. So let's do some examples of finding some inverses. And we'll look at a variety of different settings. So I'll start with like a mapping diagram. Say like 1 goes to 2, and 2 goes to 6, and 3 goes to 5 or something. This is my function f. So there's a function, right? So this function says 1 goes to 4, so its inverse then has to take 4 and send it back to 1. Everybody agree with that? And it would have to take 5 and send that back to 3. And it would have to take 6 and send that back to 2. So it's basically just reversing the direction of everything, right? Pretty easy to deal with. So this is what we would call F inverse then. Notice F inverse is a function, right? Everything in the domain is used, and each thing in the domain goes only one place. That's just like an observation that I've made. Another way we might represent a function is just generically as a set of ordered pairs. So as a second example, let's say that our function consists of these 4 ordered pairs. If I want to write the inverse for this function, well, in F, -2 goes to 4. So in F inverse, 4 has to go back to -2. -1 goes to 6. So 6 has to go back to -1. 3 goes to 8. So 8 goes to 3. And then 5 goes to 8. So 8 goes to 5. Uh-oh, what do you notice about F inverse this time? Yeah, so it's not a function. Uh-oh, SpaghettiOs. So what we're noticing here is that depending on the situation, sometimes F inverse will be a function and sometimes it won't. Luke? Because I have 8 that goes to 2 different places, right? That'd be like 8 that goes 2 places. Repeated x coordinate is basically all we had to look for there. All right, so we have inverses. We can find them, right? We've seen 2, and it's relatively easy to create these inverses, at least in these first 2 settings. Although sometimes we're getting a function, sometimes we're not. Ideally, we'd like to be able to start with our function, and before we even start looking for our inverse, be able to tell whether that inverse will be a function or not. That's going to be the goal here in a minute. I have a couple more, well, at least one more example of doing this before we get to that, though. But keep that in mind. That is something we need to address here in another minute or two. A third way we had to represent a function was with like a graph. Now, I think the easiest way to create the inverse for this is going to be to find some points on my graph at maybe some important locations, some key locations. So maybe that's 0, -2, maybe that one's 0, -3, and maybe that one's like 4, 5 or something. Whoa, that's -3, 0. And maybe that's really like, yeah, that's probably fine. Whatever. I don't care. It shouldn't matter. That's ish what that would be. Everybody's okay with that? So just kind of found some points. What I'm going to do now is I'm going to transpose those x, y coordinates. So for example, -3, 0. Why did my pen stop? There it goes. Is going to turn into 0, -3. 0, -2 is going to turn into -2, 0. And then 4, 5 is going to turn into 5, 4. Everybody's okay there? Now the key here is that the vertex of my function is also going to be the vertex for my inverse. So when I draw this, I'm going to have something that looks like this. Everybody okay with that? Again, what do we notice about F inverse here? It's not a function, right? Now, the alternative way of kind of finding an inverse from a graph is if I take the line y equals x, if I reflect my function across that line, so like this part when I reflect across is giving me that, and like this part when I reflect it across is giving me like that, and then this part when I reflect it across is giving me like that. You could do it that way as well, but I find that to be a little bit more challenging to kind of visualize what that inverse is going to look like. What I find it more useful for doing, though, is after I plot those points, is to just give it a quick once-over check to make sure, like, oh yeah, drew that right, because I can see the reflection a lot easier once I have it in there than like taking the other thing and reflecting it. It's a little bit more challenging to do it that way. Although you could, if you feel comfortable doing that, that's not wrong. But I find it much easier to just like estimate some points or pull some points from the grid anyways, and then just transpose them and plot them and doodly-doo. You know what I mean? Everybody feel okay about that? Okay. So let's sort out now how we can predict whether F inverse will be a function or not. I mean, obviously we could find F inverse and then determine whether it's a function or not. Like, that's fine. But we'd like to be able to just use our information from F to do that. We'd like to not have to find F inverse in order to be able to tell. And it's possible to do this. I need to define a few things, though, first. So we'll define a couple of terms that we'll use to do this. The first term is called onto. We say that a function is called onto if every element in its range is mapped to by some element in the domain. We say that a function is called, I forget, is. A function called, we say is called, googly moogly, one-to-one if every element in the domain maps uniquely to a distinct element in the range. And lastly, we say that a function is called bijective if it's one-to-one and onto. As a aside, sometimes the term onto, we use the term surjective instead. Onto is probably used more frequently, but not that much more frequently. And one-to-one, sometimes we use the term injective. Again, one-to-one is probably used more frequently, but not that much more frequently. I only mention that because now it kind of makes sense why we call the thing bijective if it's one-to-one and onto, that it's injective and surjective. It's bijective. It has two of these jectives. Makes a little bit more sense if we use those two names instead of one-to-one and onto, to why we got bijective from that. So let's look at some examples of some functions and decide whether these things are one-to-one and onto. And in doing so, we'll try to figure out how this is related to deciding whether something's inverse will also be a function. Okay? And then we'll get back to talking more about inverses. So let's start with a mapping diagram. So maybe 1 goes to 4, and 2 goes to 5, and 3 goes to 5. So if I look at this function, this is not onto, because I have a value in my range that's not reachable. Nothing goes to 6. I know. I also say that this is not one-to-one because I have two x values. They go to the same y value. Does everybody feel okay about looking at a mapping diagram and being able to pick out if something's one-to-one and onto? It's pretty easy, right? Let's look at what happens if we try to find f inverse of this, though. So 4 is going to have to go back to 1. 5 is going to have to go to 2. And it's going to have to go to 3. And 6 doesn't go anywhere. So if I look at f inverse, is this a function? Definitely not. Why not? So one reason it's not a function, I heard somebody say that we have an x that's going to two different y's. Notice that's a result of the original function f not being one-to-one. There's another reason, though, why this is not a function. What's the other reason it's not a function? Yeah, I have a domain that doesn't go anywhere. Right? The fact that 6 doesn't go anywhere is a result resulted because f wasn't onto. So based on this, I can conclude that if f of x is bijective, that it is one-to-one, and it is onto, then f inverse is a function. That's going to be my big takeaway. That boiling down to checking whether f inverse is a function turns into just checking to see if f is one-to-one and onto. Everybody cool with that? Let's look at some other function representations. Mapping diagram, it's pretty easy to tell. Let's look at a graph. is this graph onto? It's not. Why not? Well, I have y coordinates that don't correspond to any point on my graph, right? Whole bunch of y's that are not used by any point. Does that feel okay? Is this function one-to-one? No. Why not? Because I have some points that have different x coordinates, but the same y coordinate. Sometimes we call that check for whether a function is one-to-one a horizontal line test. Just like the vertical line test checked for repeated x coordinates, a horizontal line test will check for repeated y coordinates, or it'll check if a function is one-to-one. Sydney? Sure. Does that feel okay to everybody? So if I talk about an HLT or horizontal line test, we're just checking if something is one-to-one. Works the same way as the vertical line test, right? So at this point, you're like, okay, you've given me two examples of functions that are neither. Can you give me an example of a function that is one-to-one and onto? Sure. Well, any like linear function will be one-to-one and onto. Right? All the y coordinates are used, and they're just used one time. So this is both one-to-one. The y coordinates are only used once. And it's onto because all the y coordinates are used. Well, what if, can I have something that's one but not the other? Sure. If I have just something like this, that's one-to-one. The y coordinates that are used only one time. But it's not onto because I have y coordinates that aren't used at all. Well, can I have something that's onto but not one-to-one? Sure. How about something like this? That's not one-to-one. Definitely would fail a horizontal line test. But it is onto every y coordinate, or every y value, there's a point with that y coordinate. Because I have arrows pointing up and down, connected in between, right? Does that feel okay? Just the difference between one-to-one and onto? Really, all I'd ever expect you guys to be able to do is to look at a graph and tell me. That would be sufficient. Or look at a mapping diagram and tell me whether they're one-to-one and onto. I wouldn't expect anything beyond that. Ariana? Sure. All these y values don't have a point that associates with it, right? So like there's no point that has the y coordinate -1 or -2 or -3. So the whole range isn't covered. Is that okay? Cool. Okay. Tommy.
I think a weird way to ask, I don't know how to say it, but in your third graph,
Yeah.
it's be one-to-one if you use the horizontal line test, left side, right side. Yeah.
Well, those are 3 points that all have the same y coordinate, right? So it can't be one-to-one.
Okay.
Does that feel okay?
Yeah, that makes sense.
Teague.
So for it to be onto it, the range is to be negative infinity.
Yes, basically. Now, like, I'll say that for us right now. Technically, no, but like for what we're doing with this, yes. Is that an okay answer?
Yeah.
Okay. So like that's a much more complicated question than really I'm prepared to deal with. But for right now, yes, that would be fine. Fine way of thinking of it. forever, no, but for high school, that'll be fine. You know what I mean? And again, I try to be as truthful as I possibly can about questions like that, where it's like, no, but like, for now, that's fine. Stretching? Yeah, go ahead. All right. We have one more way to represent a function that we should talk about how to find its inverse. And that is with an equation. So let's do a couple of examples of doing that. So here's a function, and we're asked for its inverse, and we're given an equation. Now the process here is going to be a little bit more difficult than what we had with a graph or a mapping diagram or a set of ordered pairs, but not that much more difficult. So here's the way that I like to do this. I'm going to start by replacing my function notation with a y equals. And then I'm going to use algebra to get the x by itself. So in this case, I would add 7 and divide by 3. And then I'm going to swap the x and y variables. So I'm just going to change the name of all my y's to x and all my x's to y's. And then I'm going to put it back into function notation. So instead of y equals, I'll write f inverse equals. And there's my final answer. Not too bad. If you think about what we did there, we basically undid f and then switched the x's and y's, right? Which is ostensibly all we're doing before. This just we did symbolically instead of with a diagram or something. Is that okay? Now, we say that these two things are inverses. Is there a way to check this? Yeah, so if you remember back to the definition for inverse functions, if I do f compose f inverse of x, I should get x. And if I do f inverse compose f of x, I should also get x. Let's just check that now. You don't really need to do this unless you're directed to, but I think I have some questions in the homework where I ask you to check if two things are inverses or not. So our definition of composition says that f compose f inverse of x is f of x, or f of f inverse of x, excuse me. In our situation, f inverse is x plus 7 over 3. If I do f of that, I'm going to plug that x plus 7 over 3 in place of x to my function f. So I'm going to have 3. Instead of x, I'm going to write x plus 7 over 3. And then I have my minus 7. Everybody good with the composition that happened there? Okay. The times 3 cancels with the divides by 3. That leaves me x plus 7 minus 7. The plus 7 cancels with the minus 7. And we're left with just x, which is what I was supposed to get. Now I just have to check the other direction. You can celebrate. So f inverse of f of x. In this problem, f of x was 3x minus 7. When I plug that into f inverse, I get 3x minus 7 and then plus 7 all over 3. The minus 7 cancels with the plus 7, leaving us with 3x over 3. The times 3 cancels with the divides by 3, and we're left with just x, which is what we wanted. Again, if all I'm looking for is the inverse, I don't need to do this. If I was given two functions asked to prove that they were inverses, this is what I would do. Yes, of course. Okay, let's do some more examples of this, because algebraically, some of these get a little bit more complicated. And it provides us a nice opportunity to review some of the solving techniques that you guys would have done in your Algebra 2 class. So let's say we have g of x equals 2x plus 5 over 5x minus 8. This is a little bit different because I have x's in more than one location, right? That's okay, though. I'm going to still start the same way. I'm going to replace my function notation with y equals. And now I'm going to try to get the x by itself. Notice I have two different x's, so at some point I'm going to have to combine these together into a single x somehow. That's okay. We don't know how to do that right away, maybe from looking at it, but we'll get there. My suggestion for you in a problem like this would be to get rid of the fraction as our first step. So I'd cross multiply. So that gives me 2x plus 5 equals y times 5x minus 8. That's quite a bit nicer with no fraction there. I would distribute the y as my next step. Oops, 8y. And now I'm going to move the stuff with x's onto one side and the stuff without x's onto the other. So I'll subtract 5xy from both sides, and then subtract 5 from both sides. Notice on the left-hand side, everything has a factor of x in it. So I can take out a greatest common factor of x. In doing so, I went from x in 2 locations to x in 1 location. Yay! So my next step will be to divide both sides by 2 minus 5y. And there's the x all by itself. If I look at this, I can do a little bit of cleanup here to make this expression a little bit nicer. A lot of negative signs rolling around here. If I multiply the top and bottom by -1, that'll give me 8y plus 5 over 5y minus 2. You don't have to do that, but I would just to get rid of some negative signs. Like, who wants 3 negative signs when you can have just 1? You know what I mean? And then I'll swap the x and y coordinates and write it in function notation. I'm going to do that all in one step. You feel okay there? I'm going to go through and do the rest of these, and we'll come back at the end with, if there's time remaining, and maybe we'll confirm a couple of these that you feel like are the ones that look like the most challenging. But I want to do all the writing the inverse of these problems before I go back and burn a bunch of time doing that other stuff, because it's just kind of a lot of writing for those steps. And mostly they're all the same. Let's see, C, and then a F, G, H is my next letter. Yes, sir. Absolutely. Okay. We'll start by making this y equals. And to get the x by itself, what should I do first? Yeah, add 4 to both sides. Then what? Divide by 3. And then what? Square root both sides. What do you have to remember when we square root both sides? Very good. And then we can rewrite this in function notation and swap the x's and y's. Yes, sir?
Is it the same way as the square root of x plus 4 and then also the square root of 3?
Yes, that means the same thing. Yep, so if you remember from last year, we would have talked about this identity.
But if you do that, then you have to rationalize it.
I'm not going to, like, unless the answer is all numeric, I'm not going to worry so much about a rationalized denominator. Because quite frankly, that just makes this uglier, right, to rationalize the denominator here. So it's much neater and cleaner and simpler. And if we're not doing anything numerically with it, like, you could. I wouldn't mark it wrong. So if you wanted to do that, like, you're fine to do that. You could write it as plus or minus square root 3x plus 12 all over 3. You could write it that way if you want, but this is fine too. Notice here that h inverse of x, though, is not a function. The issue here, the main issue for us, is that it's not, or h of x was not 1-to-1. So like if I drew the graph for this, we have a bunch of y coordinates that are repeated, right? What I would do to make h inverse a function is I would restrict the domain on h of x to really just be 1/2 of the parabola. Whether it's the left-hand half or the right-hand half doesn't really matter. For the sake of argument, I would say, okay, I'm just going to restrict the domain to be greater than or equal to 0. What happens is when we do that, and we get to this step, I can drop the minus from the plus or minus because I know x has to be greater than or equal to 0. And that would allow h inverse then to just be this. Now you're asking, the question would be like, when would I have to do that? When do you care that I don't do that? It's a matter of directions. If the directions just say find the inverse, what we did in the red is fine. If I ask to find the inverse function, then we would have to restrict the domain and make sure that what we end up with is a function. Is everybody okay with the distinction there? It's purely a directions thing. One way isn't the right way to do it. One way is not the wrong way to do it. It's just whether you're following directions or not. And the distinction there is inverse versus inverse function. Is that okay? I think we did that last year also in our Algebra 2 class. Whether you remembered it or not is a different story, but that's okay. I don't expect perfect recall. Let's see. What HI is the next letter in the alphabet. Okay, I'll do another one here. So start by writing it as y equals. Now we want to get the x by itself. To get the x by itself, the first thing I should do is, what do you guys think? Square both sides. I agree. So it's going to be y squared equals 12x plus 5. Maybe I'll write it on this step. Okay. And then from there, what do? Subtract 5 and divide by 12. I'm going to do that all in the same step. Are you guys cool with that? Now the x is all by itself, so I can rewrite this in function notation and swap the x's and y's. And I'm done. Cool. Everybody feel okay on that one? Again, if I'm going too fast, tell me and I can slow down. Sometimes I just get excited about doing the math. You know? Plus, this is the third time I've basically done this today, and really this is like the 8th time I've done this overall or something, so it's sometimes I just get rolling, you know? If it's too much, let me know. E, and then j of x. So j of x is an exponential equation, or exponential function, I should say. J of x equals 1/2 times 3 to the 4x. Again, we'll start by making it y equals. And then what should be my first step to get x by itself? I can't multiply the 1/2 and the 3 because they have different exponents and different bases. Right? If 1/2 was also to the 4x, I could multiply them together. Or if 1/2 was a 3, I could multiply them together. But because I have a different base and a different exponent for both of them, I can't multiply 1/2 and 3 together. Is everybody okay with what I mean there? Again, just in general, we had 2 rules for multiplying exponents. So if the exponents are the same, you can multiply the bases and keep the exponent the same. Or if the base is the same, you can keep the base the same and add the exponents. That's our rule for multiplying, our 2 rules for multiplying from last year. Do you remember those? Okay, so I can't multiply the 1/2 and the 3. What should I do? Multiply both sides by the reciprocal of 1/2, or just 2. Yeah. You could also think about it as dividing by 1/2, but like, I hate dividing fractions. I'm always going to think about it as a multiplication problem. Okay. Now we got to get rid of that 3. How do I get rid of an exponent base? I use a logarithm. Which logarithm do I need to use in this case? Log base. Which one? Let me rephrase. Which would be the best logarithm to use in this case? Log base 3 to match the exponent base. Now, you could really use any logarithm in this case and it would be fine. I rephrased to say the best one because it makes the problem quite a bit easier if you use a log base that matches your exponent base, because log base 3 cancels exponent base 3. And on the right-hand side, you are left with just 4x. Which, a heck of a lot better than having another logarithm hanging out there if you used a different log. Last step would be to divide by 4. The way I'm going to write it, though, is I'm going to write it as 1/4 times I think is the clearest way of writing this. And then I'll rewrite it in with function notation and swapping the x's and y's. Also, alternatively, if you wanted to think about it as division, oops, not 3. You could write it this way, but that division bar needs to be over the whole thing. If you put it just over the log or just over the 2x, I would mark it down. But that's why I put the 1/4 in front, because there's like no ambiguity. You know what I mean? But that would be okay what I wrote in green also, if you wanted to think about it that way. Let's see, F is my next letter in the alphabet. And after J comes K. This will be the last example. After this, we'll go back and find, I don't know, 1 or maybe 2, if you guys are feeling it, of these, and we'll go back and verify that they are inverses, that we did them correctly. I mean, I know we did them correctly, because like I said, I've done this like 8 times now, or something. But just to practice using that definition of inverse to confirm. All right, so this one, k of x equals 5/3 times ln of 7x minus 1. Remember, the symbol ln is the natural log. That's what that symbol stood for. We'll start by rewriting this with a y equals. And then to get the x by itself, the first thing I should do is multiply by the reciprocal. Okay, so multiply both sides by 3/5. That's good. There's some other stuff you could do with the properties of logarithms, but this is by far and away the easier way to go about doing that. Okay, and then how do I get rid of a logarithm? I need to use a exponential base. So which exponential base should I use for the natural log? E. Remember, the natural log is log base E. So I'm going to draw like an absurdly large E here, just so that when I go back and I look at my stuff, I'm not confused that I'm multiplying by E. I definitely am not doing that. E is the base of an exponential. So the right-hand side, exponent base E cancels log base E. So I have e to the 3/5 y equals 7x minus 1. And then I add 1 and divide by 7. Everybody's good with that? And my last thing here to do would be to put it back into function notation and then switch the x's and y's. Feel okay on these? I want to do all these examples because if you think about what you did last year in your Algebra 2 class, you talked about polynomials, rational functions, radical functions, exponential functions, logarithmic functions, and we did an example with each one of these, so we kind of reviewed how to solve equations of those types a little bit. We have a few minutes left here if you guys want to pick one or two of these inverse pairs that we want to confirm. Sometimes that process can be a little bit tricky. Or is there any one of these pairs that look like you want to see it done? If not, I'll pick. Arya. Sure. So j of x was negative 1/2, 3 to the 4x. And j inverse of x then was 1/4 log base 3 of negative 2x.
I think it was just a regular one.
Oh, was I, did I write it as a regular 1/2? Sure. Whatevs. The example in my notes, I guess I had a negative. It doesn't really make much difference. Paul? Absolutely. Okay. So I need to do two compositions. I need to do J compose J inverse. And then I also need to do J inverse compose J. We'll just take them one at a time. J compose J inverse is J of J inverse of x. In our case, J inverse of x was 1/4 times log base 3 of 2x. And then what I'm going to do with that is I'm going to plug it into the x in J of x. So far, so good. Okay. So now the composition is done. Somehow this should simplify down to just giving me x. Let's see. I have 4 times 1/4 in the exponent, so those cancel out. I have exponent base 3 and log base 3. Those cancel out. Then I have 1/2 times 2x. So 1/2 and 2 cancel out. I'm left with just x. Yay! But I'm not done, because I still have to do the other direction. So J inverse compose J of x is J inverse of J of x. And in our case, J of x was 1/2, 3 to the 4x. So we're going to plug in 1/2 times 3 to the 4x into the x for J inverse. So I have 1/4 log 3 of 2. And then in place of x, I'm going to have 1/2 times 3 to the 4x. The composition is done, so now it's time to simplify. I see 2 times 1/2, so those are going to cancel out. I have log base 3 of an exponent base 3. Those are going to cancel out. I'm left with then 1/4 of 4x. 1/4 and times 4 cancel out. And I'm left with just x. Yay! Arya, do you feel okay on that? That's a good one to pick because, again, like, my experience of the Algebra 2 topics from last year, logs is one of the places where we feel the shakiest. So seeing that again is probably nice. We'll come back and do logs again in second semester in great detail, but for right now, just kind of reminding you of stuff that we remembered doing last year. Dominic.
What is the base of the common law?
10. Yeah, so if we write just log with no subscript, that is the common log. That is log base 10. Yep, good question. I feel good about what we've done today. I would do another of these if you wanted to, but if you're like, yo, I'm just ready to be done, can we stop? I get that too, and I'm happy to do that. It's been a long day, part of a long week, part of a long start of the school year. Based on the